Alright, so in this problem we have a block going up and then back down a ramp, and we have a motion sensor that's measuring the position of that block. And this problem as well, I'm going to make sure to redraw the whole thing, but this problem gives us a coordinate system which determines a lot of the signs of our problem. So let me draw the diagram so I can point out some of the key features. And our block starts right there. Its initial direction of motion is right there. We're told our coordinate system, they've already sort of done the tilted coordinate system for us, right? It's a coordinate system parallel to the ramp, and they've called that the x-axis. And this location right here is x equals positive d. And this location right here is x equals 0. And this is where we have the motion sensor at x equals 0. So, we also have angle theta. Yeah. So, this defines the positive direction for us, right? The positive direction is that way. Actually, let me do that in a different color so it doesn't stand out. So it does stand out. So the positive direction is down the ramp. That's pretty standard, but that's important because that tells us the direction and sign of our acceleration and velocity completely. So in part A, the first step is, what is the acceleration? And hopefully this is something that you just remember, because we're on a ramp and it's frictionless. And so that tells us that if I was going to do a free body diagram of my block, right, we'd have the normal force and the weight. And so in my tilted coordinate system, there are two components to the weight force, and this component right here is going to be mg sine theta in length. And so that tells us that since F equals MA, MA equals mg sine theta, or A equals g sine theta. Should be very minimal work, but again, if you just happen to remember that acceleration on ramps is g sine theta, since it says determine, you can just write that down. It's not like show that. You don't have to prove every single line. Once you have the acceleration, the other parts are hopefully very easy. It's just kinematics. If I know the initial velocity and the acceleration, I can relate that to the velocity as a function of time. Right? That's just v equals v initial plus at. And so all I do is I plug in the one thing that you have to be careful with is that the initial velocity is negative because the direction is opposite. And then gt sine theta. Right? And that's part 2. And then part 3, if I know the velocity is a function of time, or, well, actually, even more specifically, if I know the initial position, the initial velocity, and the acceleration, that's another kinematics equation. I can write the position as a function of time, right? X initial plus v, stick with initial so I don't get my subscripts confused, plus 1/2 at squared. And so, I'm kind of out of space, so I'm going to write it over here. And so really, all we do is we plug in what we know into that. Well, our initial position is given. It's, right, x equals d. So x equals d. V initial, still negative, minus v initial t, plus 1/2 g sine theta t squared. And that's it. Right? That answers part A. It should be very fast. The key is recognize the forces from the free body diagram, then you have the acceleration, and then kinematics does the rest. Point 2, develop, or part B I guess, right? Develop an expression, or derive an expression. This means you need to show every bit of work when it says derive. Derive an expression for the position, the minimum position it reaches when it's closest to the motion sensor. And so the first thing is you notice that it says express your answer in terms of a listing of things and it doesn't involve time. So we need to describe position and we can't use time. There's only one kinematics equation that does that. Right, this one. So it has to be from that. It's the thing that describes motion. It doesn't involve time. And so now we have to think about the meaning of some of these. So the point of closest approach, the final velocity, is something that you should know, even though it doesn't directly tell you. It's 0. Right? If it was not 0, then it either used to be closer in the past, because it's moving back down the ramp, or it will be closer in the future, because it's still moving up the ramp. So we have 0. This is negative v naught, but we're going to square it so the negative won't matter. This is g sine theta still, and this is x min. Right, that's what we want to find. But it's not just x min, because we don't start at x equals 0, right? It's x min minus d, right? Final minus initial position. So we can plug all that in, right, and solve. Right, v naught squared plus 2g sine theta x min minus d. Right, and that's it. Now we just have to do some algebra. Right, we have to distribute the 2g sine theta. And move the v naught to the other side. Right, so we get negative v naught squared equals 2g sine theta times d with the negative plus 2g sine theta. And actually, it's probably an easier way to do that. Let's clear that up and do this a little bit faster. So we divide instead. Right. Now we put the d on the other side, and so we get d minus v naught squared over 2g sine theta equals x min, right? And that's it. That's part B. Okay, so now that should be the stuff that's pretty straightforward, right? All it is kinematics. Part C is then we're going to make some graphs, right? And essentially, part C is graph the expressions that you found in part A. So if you mess up part A, just plot whatever you determined, right? Don't make it consistent. Don't change things. So x as a function of time, v as a function of time, and a as a function of time. And somewhat counterintuitively, I think it's almost always easier to start with acceleration. So the acceleration we found was a constant, g sine theta. We put a constant, we write g sine theta, right? Label the values. It says label them. V. It's important again to remember our velocity starts negative and ends positive. And because the acceleration is constant, it's a linear relationship. So something like this. So this is negative v naught. Right? And now x. Well, we know that from part B, we don't make it to x equals 0, right? We make it to some position x min. So we can't go through the axis, the time axis, and it's got to be quadratic because we have a constant acceleration. So it's something like this, right? Where this point right here is x min, right? Something kind of like that. Okay, so part D. Now we're introducing forces a little bit more. So we've slid down and left the bottom of the ramp. Now we're on a horizontal surface, so let's do a new free body diagram. What forces do we have? Well, we're told there's friction, kinetic friction. It's horizontal, so there's a normal force, and there's the weight force. You notice that I didn't have any force that's making it move, right? That's because it had a velocity left over from there. There's no force making it move anymore. There's just a force that slows it down, friction. And so the normal force and the weight in the vertical direction really don't do anything. They just balance each other. This just tells us, in this case, N equals mg. And so that lets us calculate the friction force. Right? k is mu k times n, which is then mu k, it's still sloppy. Eventually I'll get it right, mu k mg. But F net is just the friction force in the horizontal direction, and that equals ma. So the masses will cancel, and we'll find that the new acceleration on that horizontal surface is mu k g. And realistically, I probably should call it negative. Right? The force is in the negative direction, because that's sort of consistent with my positive direction. If it came off the ramp, this would be positive. So the acceleration is negative. So once again, we look at what we're allowed to use, and time doesn't appear in it, so we have to use the same kinematics equation we did in Part B. And we want to know when it comes to rest, so that tells us V final. Right, we get 0 equals V initial. Now, you need to think carefully about what V initial is, but I think that it's pretty obvious that if there's no friction, it's going to leave the ramp at the same initial velocity that it had. This is really an energy concept that we'll cover more later, but I think that's something that you probably have a good intuitive understanding of. So that's our initial velocity, and then plus 2 negative mu k g, that's the acceleration, and then the distance it travels, right, which is what we want to know, right there. And we just solve that for d, which is pretty simple. So we're going to get d equals v naught squared over 2 mu k g. Right? And so that's the answer to part D. So part E is definitely the hardest part of the problem, and you have to think very carefully about it. So we knew what this looked like, which I'm going to draw in blue, what the old one looked like, right? The no friction, right? Kind of like, let me see if I can make that a little more accurate. Right? This is no friction. That's our answer from part C, what the velocity as a function of time looked like. But think more carefully when there's friction. So it's going up the ramp. So it's going up the ramp. What does the free body diagram look like? Well, weight is pretty straightforward. Normal force is pretty straightforward. Friction opposes the motion, so it's kind of like so, down the ramp. But going down the ramp, some stuff changes. Now we're moving this way. Weight and normal force really don't care, but friction changes direction. And so you can see that because of this, F net is different when we go up the ramp versus down the ramp. Right, up the ramp, we have to be able to conclude that F net up is greater than F net down. Right, I don't need an exact value, but when I'm going down the ramp, the component of gravity points down the ramp and friction points down the ramp, so they sort of add and become larger. When I'm going down the ramp, they point in opposite directions, so they're going to somewhat cancel out. And since this tells us a relationship between forces, but the mass never changed, then A up has to be greater than A down, right? And that, on the velocity graph, is a slope. So, what does it have to look like now? So your first thought might be, well, it takes the equal amount of time on both parts because it's the same distance both ways, so it has to go through the middle. But that's not right, because we still start at the same velocity, so I start at the point down here. And if our slope was steeper, we have to intersect sooner, right? Kind of like that. Which also makes sense, right? If it's accelerating down the ramp faster on the way up, it's going to stop sooner. On the way down, it's going to take more time to travel the same distance because it's accelerating less. So it's going to do something, right, kind of like that. That was badly drawn. Right, kind of like that. Right, so the key is the slope has to be different, and it has to cross the axis before half the time. Right, anything like that approximately works.